Okay, I think last time we discussed the dendrimers, right? Okay, this is the most, I think, most notable example, the polyamidoamine. So basically how to synthesize is it takes the nitrogen, the functional groups, and make it into amide. Okay, I think this is just an additional informations. And for the dendrimers, we can have several concept or several way to incorporate. For example, this part here. And basically how to prepare the synthesis to produce specific dendrimers, it depends on the core molecules. It depends on the core molecules. So it depends on this. So it depends on the core molecule and the branching units, okay? The branching units. Because as you can see, the results, the core molecule will be the first, or the how to identify the dendrimer is through the core, and then it's attached to the branching units. And you will see that if suppose that we are going to add more branching units, perhaps we can take this and branching again, okay? You will see that at some point, this polymers cannot be like it has some limits, right? And perhaps it will be and when it's going to be like a ball like this, right? Or we can just take the core and branching units just one side, okay? So it's like a tree, right? Like a tree. And of course, it is also going to maybe end up until certain points, and maybe like that. Okay? The dendrimers, it's really the best way to put the dendrimers is you can think the dendrimers like we can make the surface here with some certain functional groups, and then the inside is another different kind of functional groups, and we can have a good, or that will be a good approach to surface chemistry, for surface chemistry. That's really a good way, the dendrimers. And we can also make this, okay? It's similar to the first one, the second one, but we have two branching units, okay, for from the core molecules, okay. So again, one side maybe we can attach this to another polymer. So maybe this will be attached to other polymer or other molecules, and the other part will be having, maybe this is going to have like a certain functional groups here, okay? So that's the dendrimers, okay? But basically, the dendrimers or hyperbranch polymers, in our case, in the gelations, it is mostly used for suppressing gelations, okay? To suppress gelation. So if we consider, I think last time we discussed something until here, if we consider self-condensation on the given molecules, the ABB, okay, and we take all ABB and put all together, add into the branching units, and you will see that we cannot have any network. Okay? There will be no network points, okay? Because it's keep on branch, and at some certain points, at some levels, it will stop, right? It will stop because it's too much, okay? So too much B, okay? Too much B molecules. Okay, and we cannot have any network, and the A is not enough. Okay, A is not enough. Okay, so the gelation will suppress because of the tremendous amounts or a lot of amount of the B. Okay, B functionalities. So this is the conclusions. Okay? Because too much B, then gelation will be suppressed. And there are some factors which we call the branching factors. Okay. So N is the number. Okay, how many function? It's a functional group. This is for the branching. Okay, and FBR is for the branching. Term is for the terminations. Okay, and total is the total molecules. So all the examples here is showing you how to compute the factors. Okay? So you see that this is the total is 80, and you will see that what we need is we need to have, for example, here is 12. 12 is if we compute the terminations here, okay? Here terminations. This is the branching. Okay. This is terminations, branching. So the one that has circle is the one that we do not compute. Okay. If we take a look at another example as well, you will see here. You take the termination here, branching, terminations, branching. So BR is for branching. Let me write here to give you more context. So BR for branching. The term is for the termination or the end point. So if we take so this will be the termination. Okay, this is termination. This is for the branching, and it's also branching. The one in the middle is not branching, not terminations. This is for the branching that has 3 branches. So we need to have a branching that has 3 branches. If you think, oh, why this is not a branching, it has 2 branches, right? But it's not, because this is what we want to see is the whole molecules here, the whole molecules that has 1 branch, 1 core with 3 branches. Or 3 terminations. It's branching into 3 terminations. Okay, and then the conclusions from the dendrimers and the hyperbranch polymers. This is what we have. The property, it has lower viscosity than linear chain. And then it's mostly amorphous, better solubility, high density of functional groups. We can think if we take the linear chains, okay? If we take linear chain, like that, what's happened are this is going to be easy to entangle, okay, for the linear chains. So that's why it has a lower viscosity. And then because of these properties, then the applications will be for polymer electronics, because for easy to process, and coatings because it has lower viscosity, so it's easily to attach, and then for electrolyte, okay, for the membranes, and for filtration. Okay. So membranes, usually in membranes we need amorphous and high functional materials. High functional groups, yeah, functional groups density. Also I think for filtrations also need the similar applications. Okay, that's the conclusions from the dendrimer. And then lastly, for these slides is the summary for the whole thing. For the nonlinear polymerizations. So first is the network for the polymers, or for the nonlinear. What the network means is all the chains is going to connect all together. So this is going to connect together, okay? Which in turn, as a consequences, because of the connections, it will be insoluble, it's non-meltable, okay? Or we call it the thermoset. So we cannot reprocess through the heat. And then the network, it goes through the non-linear polycondensation, or we say the gelling or gelations, or the cross-link. Usually we say this is another name, cross-link or gelation. And then it's high commercial interest, especially at the beginning of the introduction of the polymers. Okay. And we learn also the gelation theory, okay, which we learned from the gelation theory the importance of the branching, that connects and makes the network formation. And also from gelation theory, we know that the functional group will be very important. Okay? If you have more than two functional group in the backbone, then it will be the requirement to make the network formations. Okay? And then the last, we can avoid the network formations, okay, by choosing the proper molecule, or the hyperbranch, or the dendrimers, okay? And then we can suppress the gylations. Okay? We can suppress the gylations. Okay. So I think that's it for the nonlinear step polymerizations. Okay, any questions from the nonlinear? Okay. Okay, I think we can continue. Okay. So we can continue to. Oh, did I? I think I haven't put the notes right in the Moodle. Right? I will put the first two notes and then the nonlinear notes later. Okay, let's move to the next sections, which is the new chapter, the chain groove polymerization or the free radical polymerizations. Okay. So this is supposed to be the part 3 of the synthesis. Actually, there will be part 4 for the synthesis, but it's going to be after the chain groove polymerizations. So we are going to learn the definition. First, the definition, the chemistry, how it goes, the reactions, the chain transfer. Okay, that will be another term to define how the process will work, and the rate, okay, the rate of polymerization. And then we are going to see the phenomenon in the diffusion and what we call the Trumpsdorf effect. Or sometimes we call it Trumpsdorf as auto-acceleration effect. And then lastly, we are going to see the inhibitions and retardations, okay? How to make the reactions stop or make it slow. Okay, I think we can observe the beginning. So the principle. So chain growth polymerization. So from the name, the chain growth is going to be how to grow a chain, okay? A chain like in the polymer. If you look on the step polymerizations, it's called step because we take all the steps in the step group polymerizations like one by one, reactions, okay, and take it slowly. Okay. Sometimes we call the step growth as a stepwise polymerization. Okay. But in chain growth, the growth for the chain, it will be very fast compared to the step. Okay. So if you see how it goes, so suppose that we have, let's say you are playing a basketball, okay, or maybe imagine if the ball is in your hand here is very hot. It's very hot. Maybe the ball is put in the middle of the field, and then it was really sunny day. And sometimes when you put the ball, it's still hot, right? But maybe imagine it's really hot. Like you cannot really touch the ball for more than 5 seconds. So after 5 seconds, you need to give to your friend, to your friends. Okay? So the ball will be given to your friends like that. So imagine this is really hot. So you need to pass the ball to your friend, and then your friends need to also pass the ball to your friend, and so on, so on, and so forth. Okay? And maybe at some point there will be no other friends in the basketball court, and then the last person just put the ball in the ground. So no ball or it'll stop passing the ball at that point. So this is what is going to happen in the chain growth polymerization. This basketball here, it is we call the high energetic species, which has the high energy level. So that means that it's going to walk around or like passing the ball really fast, okay, to every person that he find the ball. Okay. And this is what is going to happen in the chain growth. Okay, so it's going to be really, really fast. If we take the graph, let's say to give you considerations, if we take the step growth and how the molecular weight is formed, let's say this is molecular weight and this is the P, okay, over time, the convergence, okay. The step growth, the more conversions you have, the high conversion you have, the chance for getting high molecular weight is really high. But it takes time, right? It takes time to build up the molecular weight for the step growth. For the chain growth, is here. This is chain growth. So at the very beginning, it has already high in the molecular weight for the chain growth. And mostly, the chain growth is happen in the final monomers. Okay, so every monomers that has the final, the double bond, carbon-carbon double bond, okay, it's frequently happen in that final monomers, and we are going to introduce some additional terms in this chain growth, which is the initiator. So this is going to plus with the radical initiation. So sometimes the chain growth we call the free radical, the other name, polymerizations. Okay, because it involves the radical, okay? The high energy species, the radical. Okay? And how to generate the radical? We need to have another substance which we call the initiator. Okay. Okay, that's the radical species definition. So they are independently existing species, and what's so unique about the radical species is because they have the unpaired electron and they are highly reactive with short lifetime. and the radical is on this position in the sp2 hybridization. If you remember, this is the sigma bond. And this is the pi bond. Or let me write here that the radical is on a p orbital. Check. Okay. This is sigma bond, and here's this is the pi bond, right? Okay. So let me give you more context on what's going on here, to give you some sense why this is such a highly reactive process. Let's just take a look what is going on. Okay. So this is a typical monomer and typical polymer. So the final monomer becomes the chain growth products. So what's happened here is we are going to have some initiator, of course, here, right? And because of the initiator, it will break down this bond, okay? And then let's focus on this first example here. Let me write it down here. So it will be so it has the unpaired electron. This is the electrons from the initiator, okay, the radical initiator. And then it will react with the another monomer. So this will be broke the bond, the double bond, and what will happen is it will connect this together. So broke the double bond and connect the two together. And then you will see that the radical is still there, okay? And then more and more monomers react with this radical, broke the bond, and then become really bond. And how this process will be is really fast. And to give you a sense why this is really reactive, for example, if we show you, for example here, let's say we are focused on the carbon, okay, here, the carbon here. So this is going to be just one sigma bond, right? On this carbon-carbon. And we say that here we have 348 kilojoule per mole for that bond. Okay? So we need that energy level to broke the bond. Okay. Now look at the monomer, the final. It has the one pi bond. Okay, see this double bond, right? And it has 614 kilojoule per mole. Okay. Now it turns out the product, it has 1, 2, 3, right? 3 sigma bond. So 3 multiplied with 3, 4, 8 will be 1044 kilojoule per mole. So what is going on here? If we see the change from 1 sigma bond becomes 3 sigma bond. So this is from 1 become 3. Okay, from 348 kilojoule per mole becomes 1044 kilojoule per mole, which denotes that the reaction is exothermic, right? Which means the reaction is spontaneous. Okay. That's supposed to give you some sense of why it's a high reactant. And then another thing is, if you think closely, this radical is always there. So if the process or the reaction is still active, the radicals will still be there until maybe the monomer is gone, probably. But for sure, if we want to make the polymers at certain molecular weight or maybe at certain level, we need to know how to stop, like how to stop this process, which we are going to see that there will be at least 4 steps in the chain growth. It begins with the initiator, okay, and then it's adding the monomers, it's propagate, and then it needs to be stopped. Okay, it need to be terminate, and then another step is there will be perhaps there will be some transfer for the radical side. Okay. So let me go through this is just a summarize for the 4 steps that we have in the chain growth. So first step is the initiation. We are going to look all the steps one by one later. So the first step is the initiation. So the first is to generate the radical species, and it's form the active chain end. So the active chain end is the one that is going to react with another monomer. Okay. And then that active chain will propagate. Okay. Will add one by one the monomer immediately. Okay. Immediately with maybe with a fraction of seconds. It's really fast. Okay. And to end the polymerization, we are going to make the active chain end fabulous. Okay. So we need to maybe give some other molecules how to terminate the active side. And there will be another term which we call the chain transfer. This chain transfer is how to transfer this radical side to another molecule or another chain, the new chain. It's also possible. Okay, so that's the previous one is the basis, the definitions, and so on and so forth. And now we are going to focus on the chemistry level for the polymerizations. So let's say we are going to, like, we begin at the previous slides, that we are going to involve the polymers with the final, to prepare the final monomers. So first, we are going to look at the first step, the initiation. Okay, so it involves the creation of the free radical active center. So that's the idea. So free radical active center. Of course, how to get this radical is from the initiator. Okay. And then we add these free radicals to the monomer. And how to generate these radicals. So, of course, you have the initiator, right? But this initiator, if we just use as it is, it will be useless. So we need to generate with some treatment for the initiator. Why? Because to generate the initiator, we need some energy level. Okay? And how to get the energy? We can get from the thermal, from the temperature, okay, to get the radical from the initiator. We can get from the UV light or the redox chemistry. That's one possibility. And the bonds in the initiator, bonds are easily broken, And usually, if you read the reactions to the nodes, which one is the initiator, usually they will give you, for example, the thermal treatment, they will give you the delta T in the reactions, maybe in the arrow, and it give you the delta T. It means that perhaps this is the initiator that used the thermal treatment. And for UV light, maybe they give you the HV for the Planck and the frequency. And redox chemistry is, you will see the reduction oxidations in the chemistry. Okay, if you see here, we have, I think this is the peroxide, right? This is peroxide. So the idea is they give you this delta means the thermal. So they give you the temperature. So this is initiator. This is initiator. Both of this is initiator. For peroxide, this is the peroxide. And this is diazo compounds. So basic idea is to broke this into half. Okay. So we have these two radicals, and that's how we get the free radicals. This is also the same. Broke the broke here, and this double bond becomes triple, and this R becomes the radicals. And the principle is to break down the bond, it's the homolysis, and there will be electron transfer. Okay, so single electron transfer. Okay. Just these two, okay, the process. Okay, the other example, and this is the real initiator. The previous one is just an example for the some functional groups. This is the example for the real initiator in the experiment. We have the benzoyl peroxide, butyl hydroperoxide, the same peroxide. So suppose that it went to be the same principle. So cut homolysis, make the radicals, okay. And this is the diazo compound. Azo bis butyronutrient. So take this, or maybe let me right here. So cut here, make it into here, make another bond, so it's become the triple bond for the nitrogen. So cut here and cut here. And then for the UV light, if you see how it goes, so it can be the left side or the right side, because this carbon is more positive, right? So it can be benzoyl radical or the phenyl radical, or the other benzoyl alkyl ether. It can be benzoyl radical, or the other part is the alkoxy benzyl radical. So it's cut there, cut there. And this is the redox process. Okay, so if you see in the chemistry sense, we see that there will be some electron transfer from the metal, right? From the Fe, from the ferrous transfer to the hydroperoxide. Then it become 3+, which have oxidated, and this peroxide become radical with the ion, with hydroxyl ion. And the same thing with the second reactions. First sulfide ion, also a redox process. But I think the first one will be very, very basic. So I think you need to know the first one. Okay? So I think I will end up until here. Let me see which part. Yeah, I will end up till here. We're going to see more on next week class, and I think next week I will prepare another, not assignment, but more like an online test to check your feedback also, and that is basically the preparation for before midterm. Okay. So hopefully you can check the Moodle next week. Okay. And I'm not sure. Do you guys already submit the discussion tree? Okay. Yeah, okay. Good. Okay. I think that will be end for today's class. Okay.